10 meters above the ground, I have a positively charged particle of 1 coulomb. In this entire region, there is an upwards pointing electric field of magnitude 5 newtons per coulomb. How long will it take the particle to reach the ground, if ever? We can model the two forces that the particle experiences. The first one is the force due to gravity, and the second one is the force due to the electric field. The force due to gravity is simple to calculate as simply negative mg. I forgot to mention, but the particle we will assume is 10 kilograms. So, for the force due to gravity, we can plug in 10 kilograms times 9.81 meters per second squared for g to obtain a force of negative 98.1 newtons. For the force due to the electric field, we can calculate that using QE. As the charge is 1 coulomb, we can plug that in, and the electric field of 5 newtons per coulomb to obtain an equivalent force of 5 newtons. So our net force is calculated to be the sum of the two forces, which equals 5 newtons minus 98.1 newtons, or simply negative 93.1 newtons. Now, as F equals ma, we can rewrite this expression and solve for the acceleration as force divided by mass, or simply negative 93.1 newtons divided by 10 kilograms, which yields negative 9.31 meters per second squared. Now we can use the equations of motion to determine how long it will take for this particle to fall to the ground. We know that the position after some time t is determined by the initial position plus the velocity initially times t plus the acceleration times t squared by 2. We can plug in the final position as 0, the initial one as 10 meters, the velocity is 0, and the acceleration as negative 9.31 meters per second squared. We can rewrite this expression in terms of t and obtain that t equals the square root of negative 20 meters by negative 9.31 meters per second squared. Plugging this into a calculator yields a time of 1.47 seconds.